Hello, my name is Krzysztof Chojnowski and I am a senior support engineer at SOMLabs. Welcome to the second part of the series of meetings concerning working with the NXP Yocto system and the I.MX8M Mini modules by SOMLabs. The topic of today's meeting is the modification of the kernel sources, including the adaptation of the device tree to the appropriate hardware configuration. At the beginning of our meeting, we will take a closer look at the Linux kernel recipe located in the Meta SOMLabs layer. Next, we'll look at modifying sources using DevTool. With this tool, we will add to the kernel configuration the drivers for modules connected to the I2C bus and introduce changes to device tree files. Finally, we will discuss the usage of basic communication interfaces like UART, SPI, I2C from Linux user space. As part of the practical exercises that we will do during this meeting, we will have the opportunity to modify and run the new version of the kernel and check how to change the entries in the device tree that add support for basic interfaces. All sources for the exercises are located in the Home Dev Exercises Workshop 2 directory on the virtual machine. Its configuration was discussed in the previous part of the workshop. The kernel used in our configuration is available in the SOMLabs repository. It has been prepared on the top of the NXP version and includes patches created especially for the VisionSOM modules and the respective carrier ports. These sources are publicly available on SOMLabs GitHub, as is the entire Meta SOMLabs layer. Let us again take a closer look at the kernel recipe located in the mentioned layer. In addition to the repository data from which the sources are downloaded and their exact version, there are also procedures that copy the configuration file. Recently, we have discussed the names of these procedures and their conditional execution depending on the hardware defined in the configuration. This time, let's take a look inside these procedures. Inside the routine associated with the VisionSOM8mm module, the VisionSOM8mm devconfig file is copied from the repository sources to the working directory as .config and devconfig. This is the kernel configuration intended for our module, and it overrides the default configuration prepared by NXP before compilation starts. To modify the kernel configuration, we have to modify this file or add our own to the recipe. We'll cover the first of these methods. In order to run the peripheral modules that are included in the webinar kit, we need the appropriate drivers. The kernel has support for all of these devices, but we need to include them in the configuration file in order for them to be compiled with the kernel sources. Modified files containing the corresponding changes to the kernel recipe are available in the Exercises Workshop 2 Lab 1 directory and can be copied directly into the recipe. To do this and skip creating the patch by yourself, go to the recipe directory and override the existing bb-append file with the file from the Exercises Workshop 2 Lab 1 directory. Then create a new Linux I.MX subdirectory in the recipe and copy the patch file to the kernel configuration file. In the next few steps, we will see how we can generate the mentioned patch ourselves and add it to the Linux I.MX recipe. So let's go to the appropriate directory and configure the terminal just like before, building the image, giving the name of the distribution and the device used. Next, we need to call the devtool modify command with the recipe name we want to change, so Linux I.MX. The sources will be downloaded and unpacked to the workspace sources Linux I.MX directory. Then we can move on to the manually editing the configuration with the following commands. The first one, make VisionSum8mm devconfig, prepares the configuration based on the devconfig file provided by us and creates a working copy of the configuration in the .config file in the kernel source directory. Another command, make menuconfig, opens a graphical interface in which we can add or remove individual kernel components and drivers. In the graphical menu, we can use the / key to find the options we are interested in. First, we search for drivers for the PCA953 module by entering the name in the search field. From the displayed results, select the option Let's PCA9532. The driver is also intended for our PCA9533 module, by pressing the key with the results number, in this case number 3. We go straight to the needed option. Now we have a choice. Attach it to the kernel with the Y key so that it is part of the kernel file, or build it as an additional module with the M key. This time let's select it as a module by pressing the M key and return to the main menu with the exit button. The exit button is at the bottom of the window. We can move between the select and exit options by pressing the left and right arrows. Next we look for the MPL3115 driver in the same way. In the results found, we can see that this module can be used in the input subsystem, which is selected by default, and in the IIO, so industrial input-output subsystem. If we want to use it in the second configuration, we choose the first result, and we mark it with the Y key, thus including it for compilation. Then we go back and select the second search result and turn it off with the N key. Returning to the main menu, we can see that now the options on the search screen are selected in the opposite way than initially, which was our intention. Finally, we search for I.MX8M So the last search result confirms that the driver is already selected and is part of the input subsystem as hardware monitoring support. Let's leave it unchanged and exit the menuconfig tool with saving the changes. The changes are made to the .config file, which is a working copy of the kernel configuration. To generate a devconfig file from it, we can use the command make save devconfig. A git status command informs us of any changes to the repository and confirms that a new devconfig file has been generated. We copy it to the appropriate directory with the kernel sources cp devconfig arch arm64 configs VisionSum8M devconfig. Calling git status one more time confirms that the changes have been applied. To save changes to the local repository, we need to call git and with the path of the appropriate file. So we add the file version some 8mm devconfig. Git status confirms that the file has been changed, but this time the changes have been added. It is highlighted in green. To commit the changes made, we call git commit, which allows us to name the new revision in the open nano editor. I suggest using the same name as in the example to avoid conflicts in the following steps. So our code revision should be added sensors to kernel devconfig. We can now save the given name by pressing Ctrl X and then by confirming with Y key. Git status confirms that the file is no longer on the modification list, and using the git log we can see that the changes have been saved. We can see a new revision with our name. After editing, we also need to call make mr proper to remove the generated temporary files to avoid compilation errors with the sources we just modified. All changes made are stored only in the local copy of the repository in the workspace sources directory where we are currently located. However, we can generate a patch from them which will be placed in the recipe and applied to the sources each time they are downloaded from the repository. The devtool update recipe -a command with the path to the meta layer and the name of the modified recipe will do it for us. After it is done, we can go to the recipe directory and see that the patch is now listed in the recipe file. Now the patch file will be applied to the sources. The patch itself can also be found in the Linux I.MX subdirectory. The summary of all executed commands can be seen on the slide. If we would build the image now instead of the kernel sources from the repository, the sources from the workspace sources Linux I.MX directory would be taken. So the ones that we just edited. Thanks to this, we could make further changes and build new modified versions. However, to check how our patches behave with the sources downloaded directly from the repository and to test the final version of the recipe, we must run the devtool reset linux I.MX command. This command will remove the workspace sources Linux I.MX location from the list of the sources to build, so they won't be compiled anymore by bitbake. We can then remove them manually by removing the directory workspace sources Linux I.MX as indicated by the message in the terminal. Before we run the image, however, we'll move on to modifying the device tree. Adding drivers to the kernel is not enough to keep the connected drivers properly handled and running. In the case of interfaces such as I2C, UART and SPI, we have to inform the system ourselves that the driver should be loaded and provide the necessary data for its configuration. This is what device tree files are used for, which next to the kernel file are an essential element needed to correctly boot the system. The device tree files for the I.MX8M module are located within the kernel sources in the ARM64 boot DTS freescale directory. For our hardware configuration, 3 of them are required. The I.MX8M DTSI file with the module description, the I.MX8M CB DTSI file containing common definitions for the carrier boards family for this module, and finally the I.MX8M CB STD DTS file describing the board Vision CB8M STD. The first 2 of these files have the DTSI extension and are appended to the last one with the DTS extension. Together, all these 3 files form a complete configuration of the specific carrier board with the connected module. We could apply changes to the device tree in the same way as in the previous exercise with the configuration file. However, for the sake of simplicity, this time we will use ready-made patches from the Exercises Workshop 2 Lab 2 directory. Let's copy them from the appropriate places in the recipe next to the patch we recently created in the Linux I.MX recipe and replace the Linux I.MX5.4bb append file with its new version from the lab 2 directory. The latter may need to be modified if the kernel configuration patch name we put manually in the last exercise is different from what was suggested. Finally, the kernel recipe directory should look like this. It contains a modified recipe file with the bb append extension and patches numbered from 1 to 6. We will now discuss the individual changes to the device tree for each interface step by step. Although we could build a new version of the system after modifying each interface, we will only do it once at the end after discussing and implementing all the changes to avoid the need of multiple system compilations and installations. I also encourage you to read the patch content to have a full picture of the modifications made for the device tree, as some details have been omitted in the slides. The changes for the UART have been made in the I.MX8M CB STD DTS file and are divided into 2 main parts. First, the RX TX pin definitions were added according to the macros available in the I.MX8M pinfunc H file. The values on the right define the setting of, among others, the pull-up, pull-down resistors inside the CPU and should be verified with the I.MX8M Mini reference manual. The individual bit fields of the GPIO configuration registers are explained there. The configured pins are on the I.MX8M STD base board of the Raspberry Pi connector. These are pins 8 for TXD and 10 for RXD. The pins are configured in a device tree in the I.MX section by creating a new group. Pin CTRL UART3 defined for the new interface. The second part of the UART configuration is in the same file, but in the UART3 section added to the DTS file. For this interface, it is only necessary to provide previously configured pins in the pin CTRL UART3 group and enable the interface with the keyword OK. Details can be found in the given documentation file, which is distributed with the kernel source. The individual fields used during configuration are explained there. After building the image with these changes, we would see a new UART3 interface under the name I.MX8M in the dev directory. The other available ports are added and configured in the default image. On the newly added I.MX8M device representing the UART3 interface, we can perform reading and writing operations. The correctness of the serial port configuration can be verified by connecting any USB to UART converter to the mentioned pins of the Raspberry Pi connector. After logging into the VisionSome device, the serial port can be configured with the stty command. Calling it only with the "-f" flag and specifying the device name will show the current port settings. By adding, for example, the port speed, we will change these settings. In the same way, we can also set stop bits, parity, and so on. After setting the port, we can send data to it by using the echo command and redirecting the string to the TTY-MXC2 device. On the other side, in the converter terminal, we will see the sent string. To test the data reception, we can use the cat command, which opens the port and listens for incoming data. By typing the string on the other side, the converter, we will also see it in the VisionSome device terminal. Another interface that we will launch in the prepared patches is SPI. As in the previous case, we define a group of new pins, pin CTRL ECSPI1 in the I.MX section. 3 of the pins are assigned SPI interface function, so master input slave output, master output slave input, and the clock line, while the 4th one, corresponding to the chip select role, remains configured as a simple GPIO. Then we add the ECSPI1 interface configuration. We have here the mentioned group of pins, the pin CTRL ECSPI1 group, with the repeated chip select pin as GPIO. In the CS GPIOs field, we enter the pin number and port. And in the FSL SPI num chip selects field, the number of all chip select pins used in the configuration. The address cells and size cells field values mean that there is only one device connected to this SPI interface, which is defined below as SPI dev. So a generic SPI device using a kernel driver. Alternatively, a specific driver for the respective bus device could be specified here, then it would be loaded by Linux. Of course, adding more devices would require more than one chip select pin. After compiling these changes, we will see a new device, dev SPI dev00, which we can use again for writing and reading. We can verify this by connecting, for example, a bus analyzer to the pins of the SPI interface. Using the echo command, again, we can write a string into the dev SPI00, SPI dev00 device. All characters sent by SPI are read and decoded by the analyzer program. So it means that the configuration was done properly. The last interface we will cover is I2C. As in the previous two, here we also need to define the designated pins, but we will need two groups. The first one, pin CTRL I2C1 for the configuration as I2C pins, and the second group, pin CTRL I2C1 GPIO for the same pins but configured as GPIO lines. The first group is already introduced in the I.MX8M MCB DTSI file, so it is not included in the patch. The second group is needed for the so-called bus recovery procedure, in which the SDI line is stopped in a low state, which is explained in the documentation file I2C I.MX8M. In addition, we define also the I2C1 section, in which all previously defined pins and the bus frequency are given. Building an image with the described changes would result in the appearance of a new file, so the def I2C0 representing the I2C1 interface. The other two are already defined in the device tree and are used for the power management chip and the touchpad if connected. The devices attached to the bus can be checked using the I2C detect tool, which shows all the active addresses on the selected bus. Having the I2C1 bus configured, we can define the devices that we will connect to it. Starting with PCA9533, the RGB diode driver, we add an entry to the I2C1 sections, informing about the connected device at the address 62. The compatible field tells about the exact model of the device. Rec is to indicate the address again. Subsequent sections, here called green, red and blue. On the slide only the green section is shown. The remaining sections are of course in the patch, mean that the type of the output and the name under which it will be visible in the file system. Additionally, in the device tree file, we also need to add the LEDs PCA9532H header due to the macro used in the red, green, blue sections. After this configuration, we will see 3 new LEDs in the file system in the sys class LEDs directory. They can be controlled by writing values from 0 to 255 to the brightness file. This corresponds to setting the driver PWM output signal duty cycle in the range from 0 to 100%. The rest of the modules we're going to connect have a much simpler configuration. They just need the compatible field with the device name and the I2C address, like here for IMMA8451. It will appear on the system as sys class input 0 device according to our current kernel configuration. After booting the system in the sys class input 0 directory, we can read the file name, which contains the name of the device. We can also check the I2C1 address of the device, so it is 1C. The data from IMMA8451 is visible as events in the file def input event 0 after enabling the module by writing 1 to the file sys class input 0 enable. To the configuration of the last of the modules, so MPL3115A2, we also add the appropriate section in the I2C1 in the device tree with the compatible and rec fields containing the device name and address 60. This time after starting, we will see the module files in the industrial input-output subsystem. So in sysbus IIO devices, IIO device 0 as configured in the kernel. Reading the name and using the address confirms information initialization of the controller and the device. The measurement results are available in the corresponding files in the device directory. For example, in temp row containing the raw temperature reading. The scale files are used to convert the raw values into readable ones. In this case, to get the temperature in degrees Celsius, we need to multiply the value 329 from in temp row file by 0.0625 from the in temp scale file. Now it is time to build a new version of the image with all the changes described and to install it on I.MX8M according to the instructions discussed in the previous episode of the webinar. If we have a ready system, we can connect all peripheral modules to the I2C bus according to the table on the slide. 3.3 power supply on pin 1, ground on pin 6, and SDA and SCL signals on pins 3 and 5 respectively. All the pins can be found on the Raspberry Pi connector. First, we will check the PCA9533 module at address 62. We verify that the device is visible on the I2C1 bus by calling I2C detect -Y0. Then we go to the sys class LEDs directory and see 3 new entries there. We can write the numerical values to the corresponding brightness files in order to turn on and off each of the LED channels. So first the red one, next the green, and finally we can check the blue LED. The second device, I.MX8M is also visible on the I2C1 bus in the form of a busy address. We go directly to the directory sys class input 0 and read the file name to verify the name of the device. Then we can turn on the device by writing 1 to the enable file. Finally, we go to the dev input directory. There is the event 0 file that can be decoded with the EV-test tool. It lists all events sent by the device. We can also filter the results with the grep tool. By moving the sensor and changing the position of the accelerometer axis, we will see the changes in the values of the measured acceleration sent by the module. As the last one, we will check the MPL3115 module, a pressure sensor with an integrated temperature sensor. It's a device in the industrial input-output subsystem, and its files can be found in the sysbus IIO devices IIO device 0 directory. We can read the name of the device as usual for verification. To check the measured values, we can use the watch -n1 cut in temp row command, which will read the value of the file with the temperature measurement results every second. The starting value 332 increases when the sensor is touched. To get the temperature in degrees Celsius, these values should be multiplied by the coefficient given in the file in temp scale. The pressure measurement is similar. Watch -n1 cut reads in pressure row file. This exercise ends our second meeting of the series dedicated to the Yocto NXP system and the SOMLabs Vision SOM modules. I invite you to the next meeting, which will concern launching the Cortex M4 core and preparing the application for this core. Thank you very much for your attention.